We're going to start lecture 3.4, and this will conclude all the material for exam number 1. We'll be doing a general review at the end of this lecture. Okay, so we're going to start with our normal review questions, and I would remind you that all of our review questions at the beginning of the lecture are going to be from previously seen problems, so you don't have to ever worry about writing down those questions or answers. We're going to get to chemical stoichiometry, which is essentially how chemicals relate in a chemical reaction. Essentially, they relate to what are called mole ratios, which are equivalent to the coefficients in the balanced equation. I'll wait till we get there and talk about that a little bit more. And then when it comes to mass-to-mass calculations, that's where we can ask how many grams of A are produced from so many grams of X. And often we may be given masses of both reactants, at which point we have what's called a limiting reactant problem, meaning that one's going to be in excess and the other one is limiting. It's limiting how much you can make. We're going to finish with theoretic yield, actual yield, and percent yield, and then do our review. Okay, to get warmed up, we're told a sample of an aluminum compound was found to contain 32.38 grams of aluminum and 28.8 grams of oxygen, and we're asked for the empirical formula of the compound. Well, first we're going to take those masses and line them up along the left, and then in our first step we're going to convert these masses into moles using their molar mass. Going from grams of aluminum, we get 2 moles of aluminum. Using the molar mass of oxygen, we go from grams of oxygen to moles of oxygen. Now, these number of moles is the mole ratio. They're just not whole numbers. So, step 2 is trying to generate whole numbers. We begin by dividing each by the smaller of the 2 numbers. So that will be the 1.2 moles. That gives us 1 aluminum and about 1.5 oxygens. Now, that 1.5 isn't a whole number, but it looks like the fraction 3/2. So we're going to multiply everybody by 2 so that we can hopefully generate whole numbers. And sure enough, when we multiply both by 2, we get 2 aluminums and 3 oxygens. And at this point, this is the atom ratio in the compound. In other words, this is our formula. Al2O3, 2 aluminums and 3 oxygens. So again, those numbers of moles is the subscripts in the chemical formula. We're told combustion analysis of 2.40 grams of toluene, which is an organic solvent, yields 8.023 grams of carbon dioxide and 1.877 grams of water. What is the empirical formula of the toluene? Whenever you have a combustion reaction, you have carbons and oxygens that combine to form carbon dioxide, and then the hydrogen and oxygens combine to form water. So what we're going to do is very similar to what we do in most empirical calculations, only we're going to get moles of the carbon dioxide and moles of water in our first step. Now there's 1 carbon in each carbon dioxide, so our number of moles of carbon dioxide will be the same as our number of moles of carbon. But there are 2 hydrogens in water, so our number of hydrogens will be twice the number of moles of water. At this point, we're doing what we normally do. Try to generate whole numbers by dividing both by the smaller number. So we're dividing both by the 0.1823 moles. And that gives us 1 carbon and 1.143 hydrogens. That 1.143 is just a little too far off of 1 for me to feel safe with just calling it 1. So what fraction might that look like? Well, I take 1 and divide it by that 0.143 and I get 7, telling me this is like the fraction 8/7. So for step 2b, we're going to multiply both of these numbers by 7. And that tells us we're going to have 7 carbons and 8 hydrogens for the empirical formula of C7H8. We're told an oxide of nitrogen contains 63.1% oxygen and has a molar mass of 76.0 grams per mole. and we're asked for the actual formula. Well, if you're given the molar mass, we can determine if the empirical formula is the actual formula. Okay, well, we're going to get that 63.1% of oxygen and turn that to 63.1 grams of oxygen. Now, how about the nitrogen? Well, that would be the remaining 36.9%, so 36.9 grams. Our percents are the relative masses, and that's essentially all we need, the relative masses. All right, this is the same step 1, where we're going to convert each of these masses into moles, using the molar mass of oxygen to get moles of oxygen, and the molar mass of nitrogen to get moles of nitrogen. We want whole numbers, so we're going to divide each by the smaller number and hope we get whole numbers. When we divide 3.94 by 2.64 moles, we get about 1.5 oxygens. And dividing the 2.64 by 2.64, we get 1 nitrogen. Okay, I'm pretty sure we know that that 1.49 is like 3 halves. So we need to multiply each of these by 2, giving us 3 oxygens and 2 nitrogens. Or the empirical formula of N2O3. And don't worry if you want to say O3N2. Okay, when we add up the mass contribution of the nitrogen and oxygen, we get 26.0 grams per mole, which is the actual molar mass. So the empirical formula is the actual formula. When propane undergoes complete combustion, the products are carbon dioxide and water. We're asked to balance the reaction. Okay, we begin by asking, is there anybody we should leave for last? And that would be the oxygen. Okay, let's start with carbons, 3 on the left and 1 on the right. The least common multiple of 3 and 1 is 3, and whatever your least common multiple is, that's how many you put on both sides. Right, our least common multiple this time is 8. So we make sure we have 8 hydrogens on both sides. Now we've got carbon and hydrogen, so let's do oxygen. And we're going to count the oxygens on the right, and even or odd, we're going to force the O2 on the left to balance. Okay, in carbon dioxide, we have 3 times 2 for 6. And the water, we have another 4. That's 10. Yay, that's an even number. So 5 O2s. I would remind you, if you have an odd number like 9, you would write 9 halves of O2, and then multiply the whole equation by 2. The catalytic conversion of ammonia to nitric oxide is the first step in a 3-step process which ultimately results in nitric acid. Balance the equation. Okay, again we begin by asking, is there anybody we should leave for last? And oxygen again would be good for last. It's our only single appearing element, and we do see 2 compounds on the right that have oxygen in it. Both of those reasons means oxygen should be left for last. Okay, let's start with nitrogen. 1 on the left, 1 on the right. Our least common multiple is 1, so 1 nitrogen on both sides. Then hydrogen, 3 on the left, 2 on the right. Our least common multiple would be 6. So how many hydrogens go on both sides? 6. Now I erased my coefficient of 1 in front of ammonia, which is kind of a reminder somebody else was banking on that to balance, and that would have been the nitrogen in nitrogen monoxide on the right, so it looks like I need to change its coefficient. And now let's count oxygens on the right. I have 2 from the nitrogen monoxide and 3 from the water, so that's a total of 5. Being an odd number, I write this as 5 halves, because 5 halves of 2 is 5. This means my reaction is balanced, but I just need to clear that fraction by multiplying the whole equation by 2. And hence, 4 ammonias react with 5 O2s to form 4 nitrogen monoxides and 6 waters. Hydrazine is a fuel used to power rocket engines. It's a product of the reaction between ammonia and bleach. By the way, that's a very dangerous reaction. Never mix ammonia and bleach. Balance the equation. Okay, anybody we should leave for last? And I'm thinking that chlorine. Okay, let's start with nitrogen. 1 on the left, 2 on the right. Hartley's common multiple of 1 and 2 is 2. So 2 nitrogens on both sides. Then let's do hydrogen. I see 6 on the left and 6 on the right. Well, you know, maybe I should do oxygen next since I have 2 sources of hydrogen on the right. Okay, so let's do oxygen. 1 on the left, 1 on the right. Let me go ahead and put coefficients of 1 there. And now hydrogens. 6 on the left and I've got 6 on the right, so hydrogens are good. And then chlorine, 1 on the left and 1 on the right. So now my reaction is balanced. Whenever I have charged species, then I make sure that it's charge balanced, and I have 1 negative on the left and 1 negative on the right. We can always double check. 2 nitrogens on the left, 2 on the right. 6 hydrogens on the left, 6 on the right. 1 oxygen, 1 oxygen, 1 chlorine, 1 chlorine. Yep, we're good. It's always good to be able to have confidence. Okay, on to new material, and we're going to begin with chemical stoichiometry, and that's simply the word that refers to the relationship of chemicals in a chemical reaction. Now, ultimately, they initially relate through moles, and then through moles, they relate through masses. Now, let's look at some practical questions that might come up about the reaction between nitrogen and hydrogen to form ammonia. We might be asked, how many grams of ammonia can be produced from 100 grams of nitrogen reacting with 100 grams of hydrogen, as an example. Or maybe I want to form 100 grams of ammonia, and so how many grams of nitrogen and hydrogen should I react to form it? Or maybe I have 100 grams of nitrogen that I'm going to react. Well, how many grams of hydrogen should I react with it? So I hope that you can see there's all very practical questions asking about the mass of somebody that gives the mass of somebody else. These are examples of mass-to-mass calculations, which are a form of stoichiometric calculation. The relationship of any chemical to another is what stoichiometry is referring to. Now, it all begins with molar ratios. We're going to find that in a balanced chemical equation, the coefficients in front of the elements is the number of molecules, or the ratio of molecules. So that first chemical is methane, and so we can say it's a 1 molecule of methane to 2 molecules of oxygen ratio, forming 1 molecule of carbon dioxide and 2 molecules of water. Now, what's true for molecule ratios would be the same for a dozen ratio or a mole ratio. So in other words, we can say 1 mole of methane per 2 moles of oxygen, or I can flip it the other way around and say 2 moles of oxygen per 1 mole of methane. Okay, so from this balanced chemical equation we get a lot of conversion factors, a lot of molar ratios. Starting with methane, we have 1 mole of methane per 2 moles of oxygen, or 1 mole of methane per 1 mole of carbon dioxide, or 1 mole of methane per 2 moles of water. For oxygen, we have 2 moles of oxygen per 1 mole of methane, or 2 moles of oxygen per 1 mole of carbon dioxide, or 2 moles of oxygen per 2 moles of water. What you're seeing here is those numbers, those coefficients, are the mole ratio of each element or each participant in a chemical reaction. So a balanced chemical equation gives us the mole ratio. Sometimes it's called the molar interpretation, but essentially it's the mole ratio. And this is the only way we can relate one chemical to another is through this mole ratio from a balanced chemical equation. So I want to say that anytime you're given information on any chemical, so you have 100 grams of methane, how many grams of carbon dioxide are formed from it? The only way to relate one chemical to another is through moles and a molar ratio from a balanced chemical equation. I'll be saying that several times because that's important to keep in mind. The only way to relate one chemical to another is through moles. Okay, so in our first example, we're asked how many moles of oxygen react with 426 moles of methane, and there's that same balanced chemical equation. By the way, most of the time the equation isn't balanced. Well, we're using our units for this, and that begins with step 1. We're after moles of oxygen, so equals moles of O2. Then step 2, we're looking for a number with a single unit to start the calculation with, and of course that's the only number given, and it has a single unit, that 426 moles of methane. And now step 3, let's get out of that initial unit, so out of moles of methane. And now comes the big question, can we go straight from moles of methane to moles of O2? And yes, we can, since both those chemicals are in that same balanced equation. Now step 4, for the numbers, where do I get the numbers? Well, this comes from the coefficients in the balanced equation. So the 1 with the methane becomes a number of moles of methane. The 2 with the oxygen becomes a number of moles of oxygen. Or 852 moles of oxygen. Let's do another. In a combustion reaction, again, a combustion reaction is going to be some organic compound with carbons and hydrogens, maybe some oxygens, plus O2 goes to CO2 and H2O. That plus O2 goes to CO2 and H2O is common to any combustion reaction. So if you're wondering where the carbons go, they go with the oxygen to form CO2. Where the hydrogens go, they go with the oxygen to form H2O. Okay, well, we've got a calculation before us. Let's go to the beginning. We have 1 or 2 possible tools for any calculation, equations or units, and we haven't seen any equations for this, so we know we're using our units. Do we have any preliminary steps? That's a good question as well, and preliminary steps are balancing chemical equations, which we have in front of us, coming up with chemical formulas. Sometimes we have that as well, as we've seen in some preceding problems. Okay, so we need to balance the chemical equation, and we begin by asking, is there anybody we should leave for last? The oxygen. So starting with carbons, 3 on the left, 1 on the right. What's your least common multiple? 3. So 3 carbons go on both sides. Then hydrogen, 8 on the left, 2 on the right. Your least common multiple is 8, meaning 8 hydrogens go on both sides. And now let's count those oxygens on the right. 3 times 2 for 6, 4 more is 10. So 5 O2s on the left gives me 10 oxygens on the left, and now we're balanced. We can always double check if we need to. Onto the calculation, we identified we're using our units for this, and so what are we after? Moles of carbon dioxide. Okay, time for step 2. Only one number given, and moles of propane is a single unit, so it must be what we start with. And now the beginning of step 3, let's get out of that starting unit. And once again, getting this far should be pretty easy. That's the idea, to get as far as we can before we have to invest some brain power. Here comes the big question, can we go straight from moles of propane to moles of carbon dioxide? Yes, we sure can, since we have them both in the same chemical equation. And the coefficients are our molar ratio. So the 3 with the CO2 becomes 3 moles of CO2. The 1 with the propane becomes 1 mole of propane. By the way, that C3H8 is propane, if you hadn't figured that out for yourself. Or 18 moles of carbon dioxide. Now soon I want us to start asking, when we're done with the calculation, does our answer make sense? And a lot of the time we really can't tell. But sometimes we might get an answer that totally doesn't make sense. What if I had a negative 18 moles of carbon dioxide? That might not seem to make sense. What if I had 18 million moles of carbon dioxide? That also would not have made sense. So sometimes the size of a number can tell you there's something wrong with this answer. Okay, The more common calculations are mass calculations, and this would be where you might be asked what mass of product B is formed from a given mass of reactant A. So here we're given a reaction where 2 A's form 3 B's, and maybe there's some X's and Y's that are produced as well. But anyway, we might be asked what mass of B is formed from a given mass of A. Well, our first step is to take that mass of A and convert to moles of A. And the vast majority of the time when you start in the mass of a chemical, we're going to go to moles anyway. Again, the vast majority of the time, like 95% of the time. Once we're in moles of A, now we can relate amounts of A to amounts of B. So we're going to convert from moles of A to moles of B using the molar ratio from the balanced chemical equation. At this point, we're nearly home free because all that's left to ask is, can we go from moles of B to grams of B? And we most certainly can. Molar mass calculations are our most common calculation in chemistry. So if you're given a mass and asked for a mass, more than likely you have these 3 steps. Now, I would remind you one more time, if you're ever given information on one chemical, you've got 100 grams of A, and yet ask for information on another chemical, how many grams of B are formed, the only way to relate one to another is from a molar ratio step from the balanced chemical equation. So your first step, if you're not in moles, is to get to moles. And when we have other ways to get into moles, we'll have other examples of stoichiometric calculations. Okay, in our next example, we're asked how many grams of oxygen are required to react with 22 grams of propane in the following reaction. Okay, I'm going to do this one with you, and then I'm going to let you practice the next one on your own before we do it together. So where do we begin? Well, we have a calculation. We have one of 2 possible tools. If you ever get stuck, you're not sure what to do with the calculation, go to the beginning, because the beginning is always the same, and it starts like this. I've got a calculation before me. I have one of 2 possible tools, equations or units. Those are the only ways you can solve a calculation. And in this case, it's units. Then, are there any preliminary steps? And we have an equation to balance. So these are how we would always start any calculation. Okay, to balance the equation, we identify oxygen should be left for last. And we're going to start with carbons. So 3 carbons on the left, 1 carbon on the right. Least common multiple is 3, so 3 carbons go on both sides. Then hydrogens, 8 on the left, 2 on the right. What's your least common multiple? 8. So 8 hydrogens go on both sides. And now count your oxygens on the right and balance them with the oxygens on the left. 10 on the right means we need 10 on the left. Okay, we're ready for the calculation and we're using our units, so step 1 equals grams of O2. Step 2, I'm pretty sure we're starting with that 22 grams of propane. And now step 3, out of grams of propane. Getting this far should always be pretty straightforward. And now comes the big question. No big question so far, and yet we're well on our way to success. So if you've been resisting using your units, you're really making your life harder than it needs to be. This is going to be probably the most wonderful tool that you're going to learn all semester. Okay, and here comes the big question. Can you go straight from grams of propane to grams of oxygen? No. We're going from one chemical to another, and there's only one way we can do that, and that's through moles. So first in the moles of propane, then from moles of propane and into moles of the O2, moles of the guy that you're after. And now we're done dealing with the propane and we're now dealing with the oxygen. Again, the only way you can relate one chemical to another is through moles. Our last question should be nice and easy. Let's get out of moles of O2 and ask, can we go straight to grams of O2? There's our most common calculation in all chemistry. We just did 2 in the same problem. For the molar masses, for carbon I have 3 times 12 for 36 grams per mole, 8 hydrogens at 1.0 for another 8 for 44.0 grams per each mole. The balance equation says how many moles of O2? 5. How many moles of propane? 1. And then O2 is twice 16.0 for 32.0 grams per each mole. And if you're not doing this on your calculator with me, you should stop and practice some of these just to make sure that you're using your calculator correctly. Believe it or not, some simple mistakes crop up when you're using your calculator, and we don't want to find that out in the middle of an exam. Okay, so I get 80 grams of oxygen. Does our answer make sense? And it seems reasonable. Am I 100% positive I've made no mistakes? No, I don't have that luxury, but at least I know that it's a reasonable answer, so I can have a good amount of confidence in it. So we saw we went from grams of propane to moles of propane using the molar mass of propane. Then from moles of propane to moles of oxygen using the molar ratio on the balance equation. And then moles of oxygen to grams of oxygen using its molar mass. So those 3 conversions took us where we wanted to go. And as promised, I'm going to let you work on this problem by yourself for a little while. And when you're done, we'll do it together. So I recommend you hit pause right now, and then when you're done, unpause. Okay, well, where did you begin? Well, if you went all the way to the beginning, you asked, I've got a calculation before me, I have 1 and 2 possible tools, equations or units, and it would have been units. Or you might just jump to recognizing you're using units, or you might have jumped to recognizing you have a preliminary step in balancing the equation. Okay, to balance this, I'm going to let oxygen be last and start with nitrogen. 2 on the left, 1 on the right, least common multiple is 2, meaning I need 2 nitrogens on both sides. Then oxygen, 2 on the left, 2 on the right, least common multiple is 2, and we put a 1 in front of that O2, and now it's balanced. We're using our units here, and so step 1, we're after the mass of NO, so grams of NO. And I'm sure you knew we're going to start with that 48 grams of O2, since it was the only number given, and it had a single unit. This is what we normally find. There's only one number given, and as a single unit, it must be what we start with. And now on to the beginning of step 3, where we had to begin by getting out of grams of O2. Were you able to go straight to grams of NO? No, you recognize we had to go through moles, and so you first went into moles of O2. Then from moles of O2, you were able to go to moles of the NO. The only way to relate one chemical to another. And the last question should have been easy. Can you go from moles of NO to grams of NO? And I hope you found that an easy yes. O2, twice 16.0 for 32 grams per mole. In the balance equation, we see 1 O2 to 2 NOs. And NO is 14.0 plus 16.0 for 30.0 grams per each mole. And when I put this on my calculator, I come up with 90.0 grams of NO. I hope that's what you got. On to limiting reactant, and if we're given the amounts of 2 reactants, then more than likely one of them is in excess and the other one is limiting the amount that we can form, meaning limiting the amount of the reaction and how much product we can form. So let me give you an example. Imagine that I'm going to fire up my barbecue that runs on propane, and the reaction is propane reacts with oxygen. Well, do I need to worry about running out of oxygen? No, I've got so much oxygen in the atmosphere that I don't have to worry about running out of oxygen, and so the propane would be the limiting reactant. Now what if I want to do that reaction on the International Space Station? Well then, at that point, maybe the oxygen would be the limiting reactant. So a limiting reactant means that there's one that limits how much product you can form. It's going to be the one that forms the least amount of product. So here's a reaction where nitrogen dioxide and water react to form nitric acid and nitrogen monoxide. And now we're asked how much nitric acid can be formed when 125 grams of nitrogen dioxide and 95 grams of water are mixed. Now first, I need to find how much of the nitric acid can I potentially form from each of these amounts. So I take that 125 grams of nitrogen dioxide and convert it into moles of the nitric acid. So first from grams of NO2 to moles of NO2, and then from moles of NO2 to moles of nitric acid using the balanced equation. And then we do the exact same thing for the information on the water. Mass of water into moles of water, from moles of water to moles of nitric acid. Now, can I actually form 10.6 moles of nitric acid? Well, there's not enough nitrogen dioxide for this. I can only form the smaller amount. The smaller amount is the maximum that you can form. We just don't have enough nitrogen dioxide to form more than this. And so this is our limiting reactant. Now we would do an additional step to convert into the mass, which we were asked for. So step 1 equals grams of nitric acid. Step 2, start with the just calculated 1.81 moles of nitric acid. Step 3, out of moles of nitric acid. And using the molar mass, we go to grams. So we're still going to use our 4-step unit analysis procedure. I just wanted to make sure that you could see when we're done what this all looked like. Now some students, instead of just going to moles of nitric acid as we did in that first step, would just go ahead and include the molar mass to go into mass and just do it twice. But then when you're done with it. That works totally fine as well. Okay, now we're ready for theoretic yield, actual yield, and percent yield. First, what we've been calculating is the theoretic yield. So this is the amount of product from our stoichiometric calculations. So that amount of nitric acid that we just determined, that would be the theoretic yield from those two quantities of reactants. So the theoretic yield is something that we calculate, and most of our work ends up going to calculating a theoretic yield. The actual yield is the actual amount that was formed, and this is essentially done in the laboratory or given in the example problem. So you may be told the actual yield and then asked for the percent yield, where the percent yield, remember any percent, your subject over your total times 100%. Your subject is the actual amount that was formed. The total is the theoretic potential yield. And don't expect it to be 100%. Depending on the reaction, it can be as low as even below 50%, or maybe as high as in the 90s. But anyway, if you're asked for the percent yield and you're given this, maybe that 95 grams of water and 125 grams of nitrogen dioxide, most of your work goes into calculating the theoretic yield. You would be given the actual yield, unless you do this in the lab yourself. Put the actual over your theoretic, and of course it's going to be less than 100%. So again, you may be given the amount of reactants, gives you the amount of product, you're given the actual yield, put the actual over theoretic, multiply by 100%. And let's do an example. Okay, we're told hydrogen gas is produced in the reaction between sodium and water. 1.25 grams of sodium reacts with excess water. 0.00981 grams of hydrogen is formed. There's your actual yield. What is the percent yield? Okay, we're going to be using an equation and our units. The equation is our percent equation, and the units gives us the theoretic yield. Before we begin, do we have any preliminary steps? That's right, balancing the equation. I'm going to let hydrogen be last and start with sodium. 1 on the left, 1 on the right, least common multiple is 1, so 1 go on both sides. Then oxygen, 1 on the left, 1 on the right, least common multiple is 1, so there's 1 oxygen on both sides. Now for hydrogen, I've got 2 on the left, and, well, I've got 1 in my sodium hydroxide, and that means I need 1 more. So I need 1 more from the H2. Remember, this is the only coefficient I want to change. I don't want to change the sodium hydroxide. That's going to send me back to the beginning. So I just want to change the H2, and I just need 1 more hydrogen. So how many H2s do I need for just 1 more hydrogen? That's right, 1/2. The equation is balanced. I'm now just going to clear that fraction by multiplying the whole equation by 2. Now, I've got a calculation before me, equations are units, and we identify we have both, and this is going to begin with our percent yield equation. Our actual yield over our theoretic yield times 100%. And now, most of our work is going to go into calculating the theoretic yield. We're using our units for that. Step 1, we're after the grams of hydrogen that are formed. Step 2, we're starting with that 0.250 grams of sodium. Remember that other number, the 0.00981 grams of hydrogen is the actual yield. It's time for step 3, and you know how that begins. Let's get out of grams of sodium. And here comes the big question, and what's the big question? Can we go straight from grams of sodium to grams of hydrogen? No, the only way we can relate one chemical to another is through moles. So first into moles of sodium. Not after moles of sodium, so let's get out of that. And where do I go from here? Can I go straight to grams of hydrogen? No, I need to get into hydrogen by going into moles of hydrogen. Here's our stoichiometric step, our molar ratio step, which takes me from the amount of one chemical, the sodium, into the amounts of a totally new chemical, the hydrogen. One more step, out of moles of hydrogen, and yes, we can go straight to grams of hydrogen. The molar mass of sodium is 23.0 grams per mole. The balance equation says 1 mole of hydrogen formed from 2 moles of sodium, and the molar mass of hydrogen would be 2.02 grams per mole. And when I put this on my calculator, I come up with 0.01098 grams. I'm going to leave it at 4 significant figures, and then put that in with my actual yield into my percent yield equation. Again, actual yield was given, theoretic yield we just spent this time calculating, for an 89.3% yield. So do note we had both an equation, the percent yield equation, and our units here, and the preliminary step of balancing an equation. And we might still ask, does our answer make sense? And it seems like a reasonable answer, so I'm going to say yes. What if I had an answer like 1,005%? Would that answer have made sense? No. Okay, let's practice some of the things we just learned. In the reaction of iron and sulfur, how many moles of sulfur are needed to react with 6 moles of iron? Okay, we're going to use our units for this, but we do have a preliminary step, balancing the equation. I'm going to let sulfur be last and begin with iron. 1 on the left, 2 on the right. Here, the least common multiple is 2, meaning 2 irons go on both sides. Then sulfur, 1 on the left and 3 on the right. 3 is our least common multiple, meaning we need 3 sulfurs on both sides. And our equation is now balanced. So on to, we identify we're using our units. So step 1, we're after moles of sulfur. Step 2, I hope it's obvious, we're going to start with that 6 moles of iron. And Now the beginning of step 3, out of moles of iron. Here comes the big question, can we go straight to moles of sulfur? We most certainly can, since we have a balanced chemical equation with both sulfur and iron in it. And I see C3 associated with the sulfur and 2 associated with the iron. And 3 halves of 6 would be 9. After the last examples we've been doing, this one probably seems easy now. And now, how many moles of hydrogen gas are needed to produce 8 moles of ammonia? Well, we're going to use our units, and we're going to balance this equation as a preliminary step. We're going to let hydrogen be last and start with nitrogen. 2 on the left, 1 on the right. The least common multiple is 2. So 2 nitrogens on both sides. Then 2 hydrogens on the left, 6 on the right. 6 is the least common multiple of 2 and 6, so 6 hydrogens on both sides. We can always double check. 2 nitrogens, 6 hydrogens, 6 hydrogens. Okay, we're using our units. So step 1, we're after moles of hydrogen. And of course for step 2, we're starting with that 8 moles of ammonia. And here comes the beginning of step 3, out of moles of ammonia. And do note, these 3 initial steps should be very straightforward, usually very easy, and yet we're well on our way to our answer. Now comes the big question, can we go from moles of ammonia to moles of hydrogen? Yes, we can do that. We can relate moles of one chemical to moles of another if they're both in the same chemical equation. And I see 3 associated with the hydrogen and 2 associated with the ammonia. So 3 halves of 8 would be 12. Next, how many grams of pentane are required to produce 125 grams of carbon dioxide in the following reaction? And how about you try this on your own again? And I'm going to have you pause it. Okay, let's continue. Where did you begin? Well, you probably balanced the equation. And so we begin with carbons. We want to let oxygen be last. I hope you're starting to ask that question, is there anybody we should leave for last? And I hope you identified that would be oxygen. 5 carbons on the left, 1 on the right. So how many go on both sides? 5. Then hydrogen, 12 on the left, 2 on the right. So how many go on both sides? 12. And now I see 5 times 2 for 10, 6 more for 16. 16 oxygens on the right would be balanced by 16 oxygens on the left. Then we identify we're using our units for this. So step 1 equals grams of pentane. Then step 2, we're looking for a number with a single unit to start with. It's got to be that 125 grams of carbon dioxide. And now the beginning of step 3, out of grams of carbon dioxide. And we go straight to, now can we go straight to grams of pentane? No, we go to moles of carbon dioxide. And then moles of carbon dioxide to moles of the pentane. And then from moles of pentane, we're able to go to grams of pentane. Okay, carbon dioxide, 12.0 for the carbon, twice 16.0 for the oxygen. That adds to 44.0 grams per mole. In the balance equation, I see 5 carbon dioxides from 1 pentane. And the molar mass of pentane, 5 times 12 plus 12 times 1 for 72.0 grams per each mole. I hope that when you calculated this, you also got 40.9 grams of pentane. And did you remember to ask, does your answer make sense? And I hope that you did ask, and I hope you realize it seems reasonable, and indeed it is reasonable. Normally we have a hydrocarbon burning, which pentane, butane, propane, methane are. You would expect about 3 times the mass in carbon dioxide as the mass of the alkane. That's the name of the hydrocarbon that you burned. Okay, in the reaction of aluminum and oxygen, how many grams of aluminum oxide are produced from 95 grams of aluminum? I'm going to again recommend that you pause this until you are done. Okay, where did you begin? And you probably balanced the equation. That began with aluminum, 1 on the left, 2 on the right, least common multiple is 2. Then oxygen, 2 on the left, 3 on the right, least common multiple is 6. And I hope you remember that by erasing that coefficient of 1 in front of the aluminum oxide, it reminded you the aluminum was already banking on it to balance. So we needed to change that number of aluminums as well. And if you hadn't, if you had double checked, you would have caught that mistake. And now 4 aluminums on the left, 4 on the right, 6 oxygens on the left, 6 on the right. We're using our units, so step 1 equals grams of aluminum oxide. Then step 2, we're starting the calculation with the only number with a single unit given, the 95 grams of aluminum. I hope you're finding that your units are getting easy to use. They're always the same, and so that means that with practice and practice and practice, they just get easier and easier and easier, no matter when we go on to new material and new types of calculations. The unit analysis procedure is always the same. Okay, here comes the big question. Can you go straight from grams of aluminum to grams of aluminum oxide? No. We've got to go into moles to relate one chemical to another. So first in the moles of aluminum, and then from moles of aluminum to moles of aluminum oxide. That's right, this is our step to go from moles of the guy we're given information on, the aluminum, and into moles of the guy we're asked information about, the aluminum oxide. And then from moles of aluminum oxide, we're able to go to grams of aluminum oxide. And I hope you had no problem in setting this up. For the numbers, that would be 27.0 grams per each mole of aluminum, 2 moles of aluminum oxide from 4 moles of aluminum, and then the molar mass of aluminum oxide, twice 27 plus 3 times 16 for 102.0 grams per each mole. And now, what would be a reasonable answer? Well, do you think you could have a mass less than 95 grams? No, if you've got at least 95 grams of aluminum, then it seems like you'd have to have a mass that's going to be over 95 grams. So that gives you an example of one answer that wouldn't make sense, a mass less than 95 grams. And what would be kind of a top end? So probably the mass of oxygen might be a little bit more than the mass of aluminum, so I wouldn't expect much more than, say, 200 grams from my product. And so when I come up with 179 grams, I see that's a totally reasonable answer. We want to learn critical thinking, and critical thinking means to look at your answer and ask, does it make sense? Or if somebody tells you something, ask, does that make sense? Or if you read something, ask, does that make sense? That's the beginning of critical thinking, simply asking, does this make sense? Okay, ammonia is produced in a reaction between nitrogen and hydrogen, a very important reaction. When 250 grams of hydrogen is reacted with excess nitrogen, 1,261 grams of ammonia is formed. Okay, good. They give us excess nitrogen, so it's not a limiting reactant problem, so that slims up our amount of work we need to do. Okay, well, we are going to use an equation to get the percent yield, but we need to balance that equation first, so let's do that. I'm going to let hydrogen be last, and 2 on the left, 1 on the right, the least common multiple is 2. So 2 nitrogens on both sides. Then hydrogen, 2 on the left, 6 on the right. 6 is our least common multiple, so there are 6 hydrogens on both sides. Now what's next? Well, what are we after? The percent yield. Can we get that from units? No, we're using our equation for that. So we're going to begin with whatever gives us our answer. And percent yield equals your actual yield divided by the theoretic yield times 100%. The actual yield was given, the 1,261 grams of ammonia that was formed. And the theoretic yield we're going to have to calculate. And let's do that now. We're using our units for this part. Step 1 equals grams of ammonia. Step 2, we're going to start the calculation with that 250 grams of hydrogen. And now step 3, out of grams of hydrogen, can we go straight to grams of ammonia? No. To go from one chemical to another, we have to go through moles. So first into moles of hydrogen. Now that we're in moles of hydrogen, we can go into moles of the guy we're after, moles of the ammonia. And now, out of moles of ammonia, can we go to grams of ammonia? This part should be easy. And molar mass of hydrogen will be 2.02 grams per mole. The balance equation says 2 moles of ammonia formed from 3 moles of hydrogen. And the molar mass of ammonia, 14.0 grams per mole for the nitrogen, 3 times 1.0 for the hydrogen, or 17.0 grams per each mole. And when I put this on my calculator, I come up with 1,403 grams, which at first look looks a little bit big. So I'm going to ask, does this make sense? But when I think about it, since the ammonia is over 8 times the mass of the hydrogen that reacted, maybe that number does seem to make sense. Let's go ahead and plug it into our original equation. Our actual yield given, the 1,261 grams of ammonia. The theoretic yield we just calculated, 14.03 grams of ammonia, and that gives us 89.9%. And so now that I have a reasonable percent, I'm going to say that's a reasonable answer. Now if that 1,403 grams was a overly large number, I might get a percent that's in excess of 100, and that would have told me to go back and check my numbers. I probably just made a simple mistake, and maybe the mistake was just the way I put it on my calculator. But again, we're not going to catch these mistakes if we don't ask, does our answer make sense? So let's start asking that question. Does our answer make sense? Okay, now we're going to go back and do a review from previous material in preparation for exam 3. What is the symbol for silver? And by the way, all these questions have been answered somewhere in your notes, so you don't have to write this down. And the symbol for silver is Ag, argentium. Remember, Argentina is named after silver. And the element with the symbol Pb, Pb stands for plumum. Plumbing comes from this word, and the ancient Romans made their plumbing from lead. And our protons, neutrons, or electrons found inside the nucleus, this would be protons and neutrons, and which carries a positive charge, and of course that's protons. And now which element has 35 protons? Well, let me grab my periodic table. And element 35 is bromine. And what are the number of protons, neutrons, and electrons in silicon 26? Well, the number of protons, I go to my periodic table again, and I see an atomic number of 14, so 14 protons. How many neutrons? Well, that mass number is protons plus neutrons, so let me subtract 14 from the 26 for 12 neutrons. And how many electrons? Well, I don't see any charge written, so it'll be the same as the protons, 14. And what are the number of protons, neutrons, and electrons in the iron 3 ion? Well, let's see. How many protons? As I look at iron, I see an atomic number of 26. How many neutrons? Well, I'm not given the mass number here, so I can't answer that part of the question. And now how many electrons? Well, if it has a +3 charge, that means it has 3 more positives than negatives, 3 more protons than the electrons. It's lost 3 electrons. So 26 minus 3, or 23. And the name of the noble gas in period 3. And so the noble gases are the far right column, period 3, and they cross at argon. And the halogen, that's group 7A in period 4, and that would be bromine once again. And now what's the expected form of the compound formed between sodium and chlorine? Okay, well, sodium forms a +1 ion, so it has a bonding number of 1. Chlorine forms a -1 ion, so it also has a bonding number of 1. There's step 1. Step 2, the least common multiple of 1 and 1 is 1. Now that 1, that least common multiple, is telling us something very important. This is the number of positives and the number of negatives. So if we realize we have 1 positive and 1 negative, we can tell that means 1 sodium and 1 chloride. Actually, at this point, chlorine is turned into chloride because it stole an electron from sodium. What about magnesium and chlorine? Well, magnesium forms a +2 ion, so it has a bonding number of 2. Chlorine is still bonding number of 1. Least common multiple this time is 2, telling us +2 is balancing -2. So how many magnesiums? And how many chlorines? What about aluminum and sulfur? And at any time, if you want to practice some of these on your own, just hit pause and start it up when you're done. Aluminum forms a +3 ion. I can see that aluminum has 13 protons, and it wants to be like neon with 10 electrons, so it hence would lose 3 electrons, form a +3 ion. Sulfur has 16 protons, but it wants 18 electrons to be like argon, so it's going to gain 2 electrons. So lose 3, bonding number 3, gain 2, bonding number of 2. Least common multiple of 6 tells us +6, which is going to take 2 aluminums. This balanced by -6, which takes 3 sulfides at this point. The sulfur has stolen the electrons and become the ion sulfide. And hence that's the formula of aluminum sulfide. Okay, what about hydrogen and oxygen? Well, hydrogen wants to form 1 bond, so bonding number 1. Oxygen wants to form 2 bonds, so bonding number 2. Least common multiple of 1 and 2 is 2, which tells us, well, in this case, this is the total number of bonds that are formed. And since each hydrogen only forms 1 bond, I'm going to need 2 hydrogens. Since each oxygen is forming 2 bonds, I'll need just 1 oxygen. And sure enough, that's the formula of water, that's what we would predict is formed from hydrogen and oxygen. So same procedure for molecular compounds as ionic compounds, but it's kind of for a different reason. That least common multiple, instead of being the positive and negatives, is the number of bonds that are formed. And how many covalent bonds does nitrogen want to form? Well, what does nitrogen want to do when it reacts? It wants to be like its closest noble gas, and that would be neon. And so it needs to gain 1, 2, 3 electrons. Again, neutral nitrogen has 7 protons and 7 electrons, but it wants 10 electrons to be like neon, so it had to gain 3 electrons. If it wants to gain 3 electrons through bonding, it's going to have to form 3 covalent bonds. Remember, the number of bonds formed is equal to the number of electrons desired, which is the bonding number, by the way. Okay, what is forming the ionic compound containing the sodium ion and the sulfide ion? Well, those charges are our bonding numbers. Least common multiple is next. +2 means 2 sodiums. -2 means 1 sulfide. Lithium and bromide both have a bonding number of 1. Least common multiple is 1. +1 is balancing -1. And no, you don't have to put the 1s in, but this is illustrating how many there would be. Okay, bonding number of 2 for calcium, 2 for oxygen. Least common multiple of 2 and 2 is 2. So if you've been thinking that you can simply cross multiply the bonding numbers, is that working here? No, it's not. if that would work all the time, I would have shared it with you. But no, that's a generalization. That doesn't work all the time. So let's go through the full procedure to get the formula. And now, what's the formula of cyanide? Well, is there a cyano element? No, this is one of those two polyatomic ions with an "ide" suffix. Almost all of the other, meaning the polyatomic ions on the other list, had an "ate" suffix. And they all have an "ite" or an "ate, except for these two, cyanide and hydroxide, where we had two elements with a negative charge. The two elements in cyanide were carbon and nitrogen, and again a -1 charge. The other polyatomic ion with an "ide" suffix is hydroxide, which is OH with a -1 charge. Okay, there is a element, sulfur, and sulfur wants 2 electrons. Become like its next noble gas. Again, I normally means a single element ion. Ites and ates, those are the ones with the oxygens in them. And now nitrate, well, we look for the position of nitrogen in the periodic table. And so we see it shows up in period 2. Remember, if you're in period 2 or group 7A, note that looks like a 7, period 2 or group 7A, those elements have 3 oxygens for the 8 suffix. And nitrate's one of those, so 3 oxygens. And it has a negative charge equal to the bonding number, but it's one of our 2 exceptions, so we reduce that by 2. So the bonding number of nitrogen is 3, it is one of our 2 exceptions, so 3 minus 2 is 1. So nitrate has a -1 charge. Okay, what's the name of this compound? Well, it's ionic, and I can tell that because it begins with a metal. What's the name of that metal? Barium. Does barium get a Roman numeral? Yes, it does. We'll even, oh, actually, no, it doesn't. It's a group 2A metal, so it's always just barium. And now the name of the anion, nitrogen all by itself, is nitride. Altogether, barium nitride. And the name of this compound, again, I see a metal, so it's ionic. What's the name of that metal? Iron. And does iron get a Roman numeral? Yes, it does. We'll leave an empty spot behind for it. And the name of the anion, oxide. Okay, so iron, Roman numeral, oxide. What's the expected charge on the oxide? Three -2s is -6. And -6, of course, must be balanced by +6. When we divide that by the 2 irons, each one is +3 for iron, Roman numeral 3, oxide. And now what is the name of this compound? Well, what's the name of that cation? Cobalt. And it gets a Roman numeral. Name of the anion. Well, how many oxygens does phosphate have? 4. So there's phosphate. The charge on the phosphate is -3, the same as the bonding number of the phosphorus. It's not one of our 2 exceptions. And -3 is balanced by +3 for cobalt, Roman numeral 3, phosphate. I see a metal, so this is ionic. What's the name of that metal? Tin. Does tin get a Roman numeral? Yes, it does. Name of the anion, oxide again. And each oxide is -2. 2 -2s is -4. So that tin must be +4. Or tin, Roman numeral 4, oxide. Okay, what is the name of this compound? I see a metal, so that means it's ionic. What's the name of that metal? Silver. Does silver get a Roman numeral? No, it's part of that little triangle area that has a constant charge. I would remind you that was silver +1, zinc and cadmium +2, aluminum, gallium, and indium +3, and gallium and indium weren't on our list of elements that we had to know the names of. So if you do see one of these metals, then it's just the name of that metal, no Roman numeral. And the name of the anion, sulfur all by itself, is sulfide. Altogether, silver sulfide. I see a metal in a polyatomic ion. What's the name of that metal? Potassium. And the name of the polyatomic ion? Well, we begin by asking how many oxygens does phosphate have? Phosphorus isn't in that 7. Again, the 7 is period 2 in group 7A. So phosphate has 4. Well, here's 1 less, so that means this is phosphite. Altogether, potassium phosphite. And I hope you recall what you were taught about those polyatomic ions. And what is the name of this ionic compound? And I know it's ionic because it has a metal in it. Well, what's the name of the metal? Lead. And lead gets a Roman numeral. What's the name of the anion? Nitride. Again, single element I. The expected charge on a single nitride is -3. I'm just trying to gain 3 electrons to be like neon. 4 -3s is -12. -12, of course, must be balanced by +12. When we divide this by the 3 leads, each is +4. 4 lead, Roman numeral 4, nitride.